So the last two sessions we discussed about the different types of signals, the effect of noise. Then there is something called a sampling theorem. What is actually a sampling? See, when you are, let us take the example of cooking. When you are cooking and when you want to make sure that it is cooked properly, what you do is you take a few sample, okay, so some grains and test whether it is cooked properly or not. So when you feel that it is cooked, that means the entire dish is cooked enough. So you are taking a sample of it. Similarly, when you are making any analysis of, let us say, stock market simulations or quarterly losses or profits and losses of a particular company, or if you are monitoring temperature in an experiment, if you are controlling the temperature of the furnace and monitoring it every 5-10 minutes intervals, these are all called sampling, and see how the system is behaving over a period of time. What you do is you test the system for every 5-10 minutes or equal intervals of time. All these are known as sampling. So actually, by definition, it is a process of measuring the instantaneous values of continuous time signal in a discrete form. Some signal is varying continuously, say temperature of a furnace. It's varying continuously because you are heating, you are supplying heat energy to it. And you are taking the values of the temperature at different intervals of time. The time is fixed, it's not continuous. So you are measuring it in a discrete form. So there is a rule, there is a condition which says that minimum sampling rate at which the rate at which you are taking the samples in a continuous time signal, we have already seen what a continuous time signal is, that needs to be uniformly sampled so that the original signal can be completely recovered or reconstructed by these sample ones. So this is known as Shannon's sampling theorem. So sample is nothing but a piece of data which is taken from the whole data which is continuous. Okay, this is what it is. So when a source generates an analog signal, and if it has to be digitized, having ones and zeros, the signal has to be discretized in time. So that means you are converting a signal which is analog in nature to digital. This discretization of analog signals is called as sampling. This is called as sampling. Okay. So what actually are we doing here? You are converting analog signal to digital, okay, and the digital back to analog. Let us see the example. Say suppose you are connecting two computers. You have different methods of computing, half duplex and full duplex, okay. That means whether you are transmitting synchronously or asynchronously, you can connect both the computers. So if you are, let us say, you are using what is known as a telephone as a signal. You are speaking over a telephone, so your speech will be analog. That will be converted into digital because you are transmitting it through one computer, and the data or the information is processed and sent to another computer at the other end. That the information which is there in the computer is in digital form, and if a person on the other side has to listen to what you say, again the digital information has to be converted back to analog. So that means initially analog to digital conversion, so you need a converter there, analog to digital converter. Then after it is sent, again digital has to be converted back to analog, that is digital to analog converter. So this is how the signal is modulated, and we call this as modem. That is what we all use in our internet systems, modulation and demodulation. So in this process, what is it that we are doing? We are converting analog signal to digital and digital to analog. So once you are converting analog to digital, you are digitizing the signals. You are making it as ones and zeros. So by doing this, you are actually sampling. What is meant by sampling? Let us see in this example. This is a continuously varying time signal. This is the original signal. So when you are talking also, sometimes you go talk at a higher pitch, then go down, go high. It won't be uniform when you are talking. Your voice will be getting modulated depending on the words. You lay stress on some words and you will not lay stress on some other words. So your pitch, your voice will be going up and down. So therefore it is a continuous time signal. So when you take the samples, you can see some lines here, peaks, peaks, peaks and so on. So when you take the samples here, what's happening? When it is peak, it's high. When it is peak here on the lower side, this is going high. Again this is going high, so this is sampled here. You are digitizing actually. And this is, can you see it's high? Then going down, going up high. So this is how the signal is sampled at regular intervals of time. This figure indicates x of t, x as a function of time t is sampled. The second one, the first signal is original signal. The second signal is a sample signal. Okay. So if this t is multiplied by a periodic impulse train, the sample signal is obtained. Let's take a few definitions here. One is sampling rate. So you are converting analog signal to a digital signal and you are collecting the samples at some regular intervals of time. So the gap, what is this interval? That is a gap. This gap between the samples should be fixed. Okay? And the gap is termed as sampling period, which is reciprocal of the frequency, sampling frequency. Okay? The sampling rate denotes the number of samples taken per second or for a set of values. And this sampling rate should be such that there should not be any loss of information. There should not be any loss of information. At any different time, when the sample is collected, it should not differ from the original information. There should not be any loss of information. That is very important. And the sampling rate also should not overlap the information. Before, say, different signals are coming, before the first signal is ending, the second signal should not start. See, what is meant by overlapping here is like this. So suppose I send some information like this. The information is ending here. The second information should start something like this. There should be some gap, continuous time. So when you are taking a sampling here, so this is high, then when it is ending, give some time. Here you should take a sample. If you take it here, the signal is ending here, another signal is coming, there is a gap. You should give some gap there. If you don't give, what happens? The information will be overlapping. You get like this. Sampling will not be proper. So this is the rate at which the sampling is collected, and this is referred to as Nyquist rate. So this is how the sampling is done. So to understand this better, let us consider the data limits over which the sampling is taking place. So to understand this, let us see what is an important consideration in communication systems. What is an important thing is how fast can you send the data? You are sending the data, how fast? And the rate at which you are doing is a sampling rate as we discussed, and it is measured in bits per second. And when you are sending the data, there is something called as a channel in between over which the information is sent. So the data rate depends on the bandwidth, that is a channel width, the strength of the signal and quality of the signal. These are the three factors on which the signal rate or the data rate is dependent on. So there is something called as Nyquist rate we have seen in the earlier session. Now Nyquist theorem says for noiseless communication, the capacity is given by C is equal to be log of 2 power n to the base 2. C refers to the capacity in bits per second, B the bandwidth in hertz, n refers to the number of levels. So a digital signal can be represented by more than 2 levels. That is, we can send more than 1 bit for each level. So let us take this, look at this figure here. This is a digital signal. All digital signals are represented by this train of pulses. So this is referred to as a train of pulses. So in this case, this is giving a signal with 2 levels, 1, 0, 1, 1, 0, 0 and so on. Now you understand this with respect to this. You have level 1, level 2, level 3, level 4. You can see different levels here. These are 2 levels. This is 0 level, this is 0 level. Maybe if you treat this as 0 level or corresponding to 0 volts, this may correspond to plus 5 volts. Whereas here you have, this is your 0 level, 1, 2 on the negative side, 1, 2 on the positive side. Maybe this can be attributed to plus 5, plus 10, or minus 5 and minus 10. This is only arbitrary. It need not be the same throughout. So here 8 bits sent in 1 second. 1, 2, 3, 4, 5, 6, 7, 8. You can see this. This is the first bit. 1, 2, 3, 4, 5, 6, 7, 8. So you are sending 8 bits in 1 second. So the bit rate is 8 bits per second. 8 bits per second. Whereas here, how are you sending here? 1, no, this is 2 here. 2, 4, 6, 8, 10, 12, 14, 16. Here 2 bits. Then 2 plus 2, here 2, 4. So it becomes 4 here. Here 2. Here 2, here 2, here 2. 1, 2, 3, 4, 5, 6, 7, 8. So 8 into 2, 16 bits you are sending. You are sending 16 bits. Again in 1 second only. So more number of bits you are sending because levels are more. So more the levels are, more the information, and faster the rate also will be higher. So let me take this example. A digital signal has 8 levels. If there are 8 levels, how many bits are needed per level? So how do you calculate this? Number of bits per level is given by logarithm of these 8 levels to the base 2. So log 8 to the base 2 has to be, how do you write this as? This is log of 2 cube to the base 2. That means it is 3 log 2 to the base 2, which is 1, and hence it is, this is 1. Therefore, each signal level is represented by 3 bits. Okay. Another interesting example is the bit rate for high definition TV, HD TV. Nowadays we are all talking about HD TVs. It uses digital signals to broadcast high quality video signals. This screen is normally a ratio. Usually when you go to buy a TV, they will see that aspect ratio is 16 by 9. The wide, it's wider 16 and length is 9. That means there are 1920 by 1080 pixels per screen. What is a pixel? It's an intersection of a row and a column. Row and a column intersection is referred to as 1 pixel. So when you see a TV screen, this is divided into different pixels. These pixels are distributed in this wide screen 16:9. So 1920 by 1080. This is width, this is length per screen. So more, as we have seen, the number of pixels, if it is increased, you will have a fine, sharper picture on the screen. The definition is clear. So, and the screen is renewed 30 times per second. 24 bits represents one color pixel. So, how do you calculate what is meant by screen repetition? Screen is renewed 30 times per second. So, different snapshots are taken and these snapshots are continuously streamed on a TV. So, this is known as each frame is one pixel, one image is one frame. So, how fast you send these frames will give you a motion effect or a quick succession effect on the TV. So, it is refreshed at 30 times per second. 30 times frames are coming and 24 bits constitutes one color pixel. So, how do you calculate this? 1920 into 1080, that is pixels, into 30, because 30 times it is refreshing. And each color is, 24 bits represents one color pixel. So, into 24, it refers to 1 gigabits per second. So, TV station reduces this to 20. It can't afford 40. This is 1.5 into 10 to the power 12. Okay, this is 1.5 into 10 to the power 12. So, this is reduced to 20 to 40 megabits through compression. That is the best thing that is possible. Let me take another example. Suppose we want to send 265 kbps over a noiseless channel with a bandwidth of 20 kHz. How many signal levels do we need? Again, use Nyquist formula. What's given is so many kilobits per second. Kilo is 10 to the power 3. So, 1000 is equal to 2 into, because the bandwidth is 20,000. So, 2 into 20,000 into log L to the base 2. L is the number of levels. So, when you do this, this is what you are getting. 265 by 40,000. It's about 6.625. So, if log is this, L will be 2 to the power this, 98.7 levels. And this cannot be expressed as a power of 2. So, we need to either increase the number of levels or reduce the bit rate. Okay. So, it's close, let us say if you increase it to 128, it is 280 kilobits per second. If it is 64 levels, it is 240 kilobits per second. So, this is how you will be calculating the channel